Okay, I'm happy to introduce Lizy and Alan, who are going to give the talk today. This is sort of an exciting new architecture for neural networks. I have several recent papers on it. I think you're going to split the talk, right? Yeah. Okay, so whoever's going to start, go ahead.
Thanks, Adam. It is a wonderful opportunity to be here and be talking about this exciting type of neural network that we have been working on. So I'm Professor Lizy John from ECE, and this is Alan Bacellar. And so I will do the first few minutes, and then Alan will continue it after that. So essentially the problem, or why we are doing this, deep neural networks are really computation intensive and energy hungry. So they have a lot of computations, lots of weights, lots of storage, many multiplications and additions, and require significant amount of energy and compute storage. And when you think about it, we don't know how exactly our brain works. This is a model, the neurons that were created, the McCulloch's threshold logic unit neuron, is a model of how we thought the brain could be used, and we could extend that model to do the computation. So in the McCulloch and Pitts neuron model, basically we have weights, we have the neuron, we have inputs, we do a lot of multiplications, and we add them up, and we pass it through the threshold, and we have something come out. And we use many of these neurons in order to do whatever we are doing these days. And one of the things in this model is, basically all of these synapses or the synaptic connections are terminating at the neuron soma, as you would compare it to brain. But in the actual brain, the central nervous system, basically the majority of synapses are terminating on the dendrites, and that there is dendritic integration. But every computation is not basically at the neuron. So dendritic computing, or maybe an alternative, if we are looking for more energy efficient, more computation efficient ways to accomplish the same tasks we are doing. And this is a slide, the picture is from Benjio's 2017 presentation. I added a little bit of text on the left side, but basically his slide said the brain is about 500,000 times more energy efficient than an NVIDIA P100 GPU. My most recent PhD graduate, he went to NVIDIA, he said, oh, don't say that number, that's not right, and you can calculate. And so I said, you calculate and you give me a number. So he calculated and he gave me a number, 13,000. I said, that's damn good still. 13,000 is a large, there's a lot of room for us to improve. So, in order to improve, and there are other reasons also when you compare the human brain and modern chips, the brain, yes?
So the human brain, I guess, is probably not going to be more powerful, probably more, but not at a very good rate. But for this, if we follow the typical Moore's law, do you think how many years do we see they have comparable energy efficiency or never?
It is probably, if we continued what we are doing, we probably will never get it.
Okay.
If we continued what we are doing. Because also, so we may have to do something else, because it's clear how we have digitally modeled the neuron and put many of them to create that function that's actually happening, which we don't understand. But we think that's from whatever we know from neuroscience or wherever, and we created a model. But if we continue the same thing, we probably will never reach that energy efficiency. But either new kinds of models that's one avenue to go, try to reach there. Will there be some technology like superconducting or something else that will come and change everything that we will get the energy efficiency? I do not know. All technologies that we are looking at have many problems. Superconducting is a promising one, just the computations alone can be efficient, interconnect is efficient, but the cooling cost required for superconducting is very high. But that still doesn't tell that it is impossible. Maybe there are ways to reach there with technology, but there may also be, or we should also algorithmically think how to improve what we are doing. Right?
Thanks.
Yeah. And there is another way, people have compared chips and human brain. So the brain, roughly 100 billion neurons, that's what we think. And chips also contain more than 100 billion transistors. Chips are actually switching a lot faster, 1,000,000 times faster than the brain. Brain apparently, it is thought it switches like 1,000 times per second or thousands of times. But the brain has very high energy efficiency. One difference between chips and the brain has been chips, digital chips, we have very limited fan out. The way, at least how they are designed now. One transistor can only feed 4 or 6, definitely less than 10 transistors. You cannot feed 1,000,000 transistors. Whereas the brain, or even 10,000, the brain is thought to have from one neuron, it has like 10,000 connections. So technologically we can try to see whether there are other technologies or other ways to design circuits that can give more connections and perhaps we can improve something, but we do not know yet. That's another avenue to achieve this efficiency, perhaps. Now, looking at this dendritic integration, maybe there are, others have thought about it. There are papers and books that try to talk about other models and the biophysics of computations and what in the brain and what exactly happens. But one interesting model is this way of looking at what is happening is an integration on the dendrite. Essentially here this is still thought as digital in the sense of every E, anything you see as E is an excitatory function and the I is an inhibitory function, and let us look at this because this looks even more similar to what you see here. So each excitatory function, whatever it creates, maybe there is a gate that either inhibits it or senses it. Okay? So if you think like that, you can actually come up with a logic equation that tells all of this integration that's happening, the various signals that are coming and the gates or the veto operation on each, there's a control on each of them and there can be a veto up here. So the whole dendrite, every signal that came got integrated and then it is fed to the soma, equivalent to that. So there is this book, there are publications that talk about it. And there is also some early work, the RAM neuron. So the neuron is a bit of memory and you have addresses going and you are going to read out from the locations in the RAM. So is it the same as memorizing? In some way you could say, and there is some very early work that puts this interesting idea and its application for pattern recognition. Setting all those aside and coming close to things that we do, lookup tables or memory, small blocks of memory. Let's say you have two input, have a lot of expressiveness. If you have two input variables, there are 4 locations in that table. With the 4 locations, you can have any one of 16 different combinations of things going all zeros to all ones. So 2 to the 2 to the n is the number of different things that you could potentially hold in this 4-entry lookup table, 2 input variables. And if you write them out, some of those functions are meaningful, some of those functions may be pretty uninteresting, but you can have with 2 input variables, you can have 16 different functions. Can we use lookup tables to basically when you look in the DNNs, we have arithmetic expressions. And so is it possible to use lookup tables and capture the information and learn using lookup tables rather than arithmetic functions? So use logic functions, and the expressiveness is pretty high. And so there has been this effort from the 80s where small RAMs, many of them are used to basically from the input image, and image is randomly mapped to different RAMs, because if you took one big RAM, that had to be very big in order to capture all the possible combinations. However, with the random mapping, and there has been a few other encoding techniques, and thermometer encoding is or unary encoding is used. So just to make things simple, the idea is you have memory modules that are capturing the information as logic functions, and if you are trying to build a classifier, and let us say there are 10 classes, each class will need what in their literature they called a discriminator, and this discriminator, one for each class, so there will be 10 of them for digit detection, and each discriminator contains multiple RAMs, and there are techniques, hashing techniques and other techniques to make the size of this smaller and so on. But this is the basic idea from the 80s, they call this wizard. And the challenges when it comes to making weightless, so there are no multiplications, there are only table lookups, there are no weights, there are logic functions basically. But if you try to just store all the information in tables like that, it's going to be very large. Bulk of these locations will be 0. So you can use hashing and filtering techniques to make that better. A lookup table is not differentiable. And so the success of gradient-based updates, it is hard to translate to this method. You get whatever accuracy you get, but to improve it further, there are limits and limitations. So the improving or learning based on gradients are usually hard for binary networks, and there are some ways to overcome that, and for lookup tables, it's again a problem. So we have been working on this for about 3-4 years now, and we have made some of these early improvements were regarding the hashing and making it smaller. Some of it very original weightless neural networks were one-shot learning. There is no feedback, there is no gradient, there is no going back. And we tried to learn some things with a straight-through estimator and have multiple bits during training, but at the end you have binary networks at the end. But this most recent work is about how to make lookup tables differentiable. And that is the work we actually want to present today. Alan is he's here. This was in ICML this year. And so we will, he will go with the differentiable weightless neural network. Any questions so far for me, you can ask me, or, and interrupt him.
Interrupt the middle, it's best to explain the middle and to just continue to understand something. And before explaining how to differentiate for lookup tables, we're going to explain a little more on the motivation why we want to do random neurons instead of just dot product neurons like I have in DNNs. And most of it is due to the VC dimension. So VC dimension tells you how, let's say, model complexity that a model can learn, how different functions it can behave. And if you look at the VC dimension of the one layer of lookup tables, these have been proven with an exact VC dimension, not just bounds. And it's exponential the size of the lookup table related to the number of lookup tables that you have in your layer. So when you contrast this to a DNN, or even if you binarize and make a DNN, it's huge compared if you just compare the two. A DNN has a VC dimension of n plus 1 given n inputs, but a lookup table has 2 to the n. This is exponentially more complex. And you can also think, hey, you have more VC dimension, but at the same time you have 2 to the n parameters. But once you scale the model, this difference will start to become really important. For example, if you just want to express 2 input XOR functions, how can you express this in a DNN? You need 3 neurons. each with one bias and two weights, which would be a total of 9 parameters. But if I look up table neuron, you only need one neuron, one neuron only, and 4 parameters. And as the function starts to become more complicated and bigger, these differences start to become even more significant. And the lookup table neuron has a capacity to be so much smaller compared to big DNNs. And even now we have a new work, I think this is in 2022, a work showing that biological neurons are actually non-linear. So what we're doing is just approximating a linear function for each neuron and then trying to squeeze in a nonlinearity in the end. Is not actually how our neurons work. Because biological neurons can express the sort function, which a lookup table neuron can also express. And now we'll see exactly how we're going to do a differentiable weightless neural networks, which is what allows us to break free of the one-layer architectures of the past of WNNs, and also how to learn the connections between them. Because if you want to eliminate all DNN neurons and just replace them with lookup tables, you need to not only learn the concept of the lookup tables and how to backpropagate the lookup tables, but how the lookup table is going to connect to each other. Because you cannot have dense connections like in DNNs, because if you just have a dense connection, this is going to be a huge lookup table. You need the model to be sparse in order to have a lot of smaller lookup tables. And so the first thing we're going to see is exactly how can we backpropagate the lookup table. We're going to explore 3 methods that's going to progressively build on top of each other to see. We're going to see the first one is using polynomial indicators, and then finite sequence data set, finally to the extended finite difference, which is the method that we use in the paper. Okay, so before doing everything, we need to define some terms. Let's have a lookup table U in the real space, size 2 to the end. So lookup tables can have real values inside them. Technically, we aren't going to use binary in the model, but since we can generalize to real space, we just generalize to real space. And the lookup table receives n inputs. You have an address A to this lookup table, which is a binary string that determines where you're going to address. So if you have n equals 3 and A equals 110, this determines that you want to address the position 6, and you want to return the 6 position of the lookup table. Mathematically, you can just express this as lookup table U, and you address a decimal representation of the binary string. And what we're in the string is exactly this address function. This address function A, address function A takes lookup table U and address A and returns exactly the position of the lookup table. This is discrete and there is no differential derivative. So how can we do this?
But it's a polynomial, so.
Yeah, this is what we're going to show. We can express this as a polynomial.
But I guess, like, I mean, you could try and just learn with polynomials, like very high degree polynomials, but we know that doesn't work and they overfit.
Exactly. This is the first thing that we try. That's what we're going to do. We're going to show exactly why this doesn't work.
Okay.
We can use indicator polynomials. For people who is not familiar with this, these products, you're summing over all positions of the lookup table, so k is all possible positions. These products don't return 1 only if k is equal to the address A that you want to address, and 0 everywhere else. And so this second expression is the same as the first expression. And since you have a polynomial, you can have a derivative. And so the derivative of the content of the lookup table is just 1 if you want to put if the position was accessed during training, and 0 everywhere else, which is the same as embeddings that you have in LLMs. But once the more interesting thing that we want to find out is actually how to propagate through the lookup table. And so the propagation of the bit, the one of the bits, the JF bit to address the lookup table, is just the content of the lookup table if the address A with the JF bit was set to 1, minus if you flip the bit. So you're looking what's the change that you have if you just flip one of the bits. And if you're familiar with any mathematical methods in engineering, this is just a finite difference. Finite difference means when you have a derivative, you want to express it in discrete space. You can do forward, back, or backward or central approximations, but since we are only in Boolean space, we only need to flip the bit. And this will yield exactly what we want.
Yeah, so when they train DNN, they also can pruning, like they train a big DNN, then they prune it into a smaller one. And I thought feel like the lookup table here and the pruning is there any different, like fundamental difference?
Yeah, yes, this is an issue. We're gonna see there's a method to this exactly. This is the difference. You could just prune a binary neural network down to the size of 6, for example, convert to a lookup table. However, the function that this neuron's learning only can learn n plus 1 capacity. So it's only under a really simple function. You're wasting model capacity. If you can actually learn the lookup table, you can learn much more complex function. So if you just lookup table as speedups, train a DNN, and then convert to lookup table by doing pruning and binary values, you're just wasting a lot of capacity because you're just learning a line, a Boolean line. While lookup table can learn anything, store function. For example, if you try to expect store function, you're gonna need 3 of these neurons. But lookup table, just one lookup table.
So I think they also show that for DNN we don't need to use floating point 32. We can use floating point 4 and it's still working. And
Yes.
is that the same as lookup table? Or
No, because you can expect smart functions for lookup table.
Yeah,
A DNN only learns a line. And you have layers for example B, which is a collection of multiple lines that you make the decision boundary in space. But you can only learn a line with a single neuron.
Oh no, I'm
But lookup table can learn anything. Every possible Boolean function that receives any inputs.
Right, but we know you can't learn all possible Boolean functions.
Hmm?
You cannot learn all possible Boolean functions.
Not all possible Boolean functions, but given any
The
inputs to
lookup
lookup
table-
tables, you can learn all possible any inputs Boolean functions.
Right, but the lookup table is the worst possible way to encode a Boolean function because its length is enormous.
Yes. What we should
the whole-
experiment, instead of just having a huge lookup table, you can have a collection of small lookup tables.
Okay, but I'm saying the
And
reason
this
why
was
people,
expressed
the
in the
reason
DNNs.
why people use neural networks is that it's a very compact encoding of a very expressive class of functions.
Yes.
The lookup table is the worst possible way to encode a Boolean function.
What do you mean by words?
Its length is the largest. For example, you give me any labeled set, any labeled training set.
Mhm.
I'll copy it down on a piece of paper and hand it back to you.
Yeah.
It's a meaningless classifier, but it's a lookup table.
No, because you can express extremely complex functions of just a subset of the inputs.
So maybe.
And the collection of those is,
No.
you can learn smaller models.
I'm
just
saying something
in-
trivial. If you give me a training
Yes.
set and I write it down on a piece of paper and I say, here's my classifier, it has 0 training loss. Do you
Yes,
agree that?
if
Do you
you-
agree
That
that?
would be dumb,
That would
because
be
it's a
dumb.
huge, because it's a huge lookup table.
Exactly.
But we don't want that.
Right. So my question is, how are you shrinking the lookup tables?
You don't shrink lookup tables. It's just a collection of small sparse lookup
LUT2s and
tables.
LUT6, the biggest one we have used here is only 6 input.
Okay. So how? But
Maybe
how
this image was
Yeah.
Right,
bad.
so
This
how
is
do-
not a huge lookup table, it's a collection of lookup.
Right. So my
tables.
question is,
Small.
how do you encode a function? How do you? So I have like 1,000 inputs.
Yes.
How do you break that up into lookup
Yeah.
table size 6?
Input term, encoding is what we need to say.
You don't break it down the inputs, it's just sparse connections. Just like having sparse neural networks.
Yeah.
Not pruning, but sparse from the get-go, sparse already trained. You're gonna have these but with lookup tables. You're gonna have a bunch of small lookup tables
Oh, yeah,
that only
yeah.
receive like 6 inputs.
Good. So you have a bunch of small lookup tables.
Yes,
How are they connected?
that's what we're gonna show.
That is the learning part of the learning.
Okay.
Yeah, very small, even LUT2s work.
But before just learn to connect, you need to learn how to backpropagate. Because that connection comes before the rep. So you need to send an update signal to where you want to connect it. So over here, we can express using the polynomial indicator, and you can simplify this to just 5 digits,
Yeah.
because it's just a bit flip. However, this is horrible for lookup tables, which we're gonna show, because these only look as one distance neighbors in the lookup table. So let's say you have a LUT6, we have 64 position, you only look at 7 possible positions for each bit, which is the address A itself and all possible 6-bit flips you have. So if you can fall in a lot of local minimums, and we saw this in experiments. Because if all people that's 100 distant neighbor choose the same value as you can possibly just flip 2 bits and you have a way better position to go to. So the second thing we try is just doing a generalizing finite difference to a finite direction of C-bit sets. Instead of just only looking at 1-bit flips changes, you look at all possible changes inside the lookup table and see what is the maximum direction of increase of the lookup table given the size you have, which is exactly the property of the gradient, which is the direction of C-bit set. And then once you have this, you can able to follow the greatest direction of increased ascent inside the lookup table and go there to converge. However, given we also do batch learning in DNNs, this also doesn't work. Because lookup table is non-linear. So once you do batch learning, if you just aggregate the direction of steep ascent, the possible different data points, different batches, is gonna point to different points in the lookup table. This in DNN is not a problem because it's just a linear neuron with 10 nonlinearity. So with the summation, once you aggregate through batches, they're both gonna point to a good direction, approximately, because you're doing HTD. But with lookup tables, this doesn't work because of the nonlinearity. Let's say you have one data point pointing to this direction. This is the best direction for me to go, and another one pointing down. Once you aggregate both, you're gonna point to the middle. But the middle, because we're on the other lookup tables, can be a different worst position for both. So the way to solve this is actually just to sum over all possible directions you can take a step to, but weight the magnitude of the change. So even though both are pointing in different directions, both have a second best direction. And if the second best direction of both align, they're gonna sum, and over time, over batch learning, they're going to converge to the same place, and not diverge to a worst possible location.
What is h? The function h?
Hmm?
What is the
Any
function
distance.
h? Sorry.
Any
Oh,
distance.
Hammond's.
It's too many notation to put everything in this line. And with this, now you can define, not an ideal thing, because actually running lookup tables is an NP-hard problem, but this works way better than finding difference, what we showed in the paper. Okay, so now you can backpropagate for lookup table. The question now which he asked is, how can you learn the connections of the lookup table? So the way we do this is by line doing backpropagation and inserting a weight matrix within training. So we want the connections, we don't want weights at the bottom, we want the connections to send bits and address lookup tables. But if you add weights during training to represent what is the importance of each possible connections, we can actually learn how to connect the lookup tables. So the idea is that we define a weight matrix for each possible single layer that weighs every possible input to every possible output. And doing forepass, we're gonna do discrete forepass, just like we're doing straight through estimators, which is you just take the weight that the connection that has the maximum weight associated with it. And doing backward pass is just an ad hoc derivative. This is just, you're gonna be the weights according to the gradient that has the bits that aligns with the gradient. So if the gradient wants to increase the connections, or to decrease, if the gradient wants to increase, the input is a 1, you increase the weights. If it's a 0, you decrease. If the gradient tells you to decrease the activation, if the weight is a 0, you increase, if it's a 1, you decrease. This is what the first expression shows. And for the second expression, which is the derivative of the learnable mapping, which is what's learn the connections with respect to the inputs, we just distribute this according to the softmax function. So the weights that we select in the forepass is going to have the most importance and then decaying exponentially to the less important weights. And with this, we don't have any weights and no computation inference during the inference time. We only have weights during training, but during inference, since the weights are constants, the same connection is going to be selected over and over, so we just have routing. And in actual ASICs and FPGAs, this is just routing. There's no computation needed at all. The next, also, another thing we propose is doing something called learnable reduction, which is just use a perimetric decreasing structure to make it more efficient for really tiny ASICs to do pop counts. Because pop count circuits, we found out that it's really huge when you try to run it in hardware. It's bigger than the model itself. So one thing to counter this is just trying to learn a more efficient function instead of doing pop counts again. And so here we're going to show the numbers now, experimental evaluation. We're going to evaluate this model in 4 different scenarios, FPGAs, microcontrollers, and tabular data. We're not going to have time to show everything, but we're going to show which one at a time. So because when you learn lookup tables, DWNs is actually really hardware friendly to FPGAs. If you learn FPGAs have LUT6s inside them. So the collection LUT6 inside an FPGA can represent 10 Boolean function. And because we only learn a neural network made of LUT6s, you just go one-to-one conversion to an FPGA. So you don't need high-level synthesis or doing all this complicated stuff that people try to squeeze in a DNN into an FPGA. You just do a one-to-one of your model to better log it, you deploy it. And we compare this to FIN, which is the state-of-the-art binary networks for FPGAs, which they compile everything down to Boolean, like we said, and try to express. ULink, which was the previous weightless neural network, and also this other tree. This other tree is also similar to what I said before. This one, they quantize and prune down our lookup table just to, for example, 6 inputs, and they convert every possible I/O to a lookup table. And because you want to learn linear functions, this other works, what you try to do, the LUTs, the poly-LUTs, and neuro-LUTs, is okay. If you still only receive n inputs, but you try to do future mappings to learn more complex functions, or even try to learn multiple layers of DNNs, and then convert everything down to a lookup table. And this is what we're gonna show the comparison. Another one we show is against deep logic nets. Deep logic nets is another paper, but they try to do the same thing as WNNs, but on using LUTs. But instead of representing every possible Boolean function of two inputs using a lookup table, they just go for the whole hypothesis space and wait if hypothesis is hypothesis space. And at the end, the hypothesis that have the maximum weight is the one selected. So this is a lot of results that we have. We're just gonna zoom in on MNIS, which is the most common data set that we have, and we can see in the image. Thin, which is the state-of-the-art binary network implemented in FPGAs, we have almost 100-fold improvements in energy efficiency, latency, lookup table counts. For example, they need 82,000 FPGA lookup tables to implement the network. We only need 4,000 lookup tables. And one thing that is actually really important that we saw is that you need to align the lookup table size to the FPGA size. For example, if you look at n equals 6 there, in the WM represents the size of the lookup table. N equals 2 lookup table has a smaller parameter size than n equals 6. But because n equals 6 is aligned to the FPGA size, you actually have smaller lookup tables. Number of lookup tables in the FPGA for n equals 6 compared to n equals 2. And less latency and less energy as well. And this here is just some graphs for you. The smaller the better in every case, we are red, thin is in blue. And this one is comparing to logic nets, neural LUTs and poly-LUTs, which is the one that gets a proof DNN and convert to lookup table. And also you can see here, we have 100-fold improvements in average products and everything compared to that, while matching networks. There's the one. We also did ASICs for really ultra low cost implementations. We compared to a Nature paper in 24, which they try to implement tabular data using tiny classifier circuits. They do this by genetic algorithm, by just trying to, with genetic algorithm, increase the size of the circuits that you have up to a certain point and see how much accuracy you got. And we also implemented deep logic nets, which the goal of them is to learn a logic circuit. And compared to them as well, we have best accuracy in every case and smaller circuit size in every case. And also, last experiment we did is just, what if we train DWNs on tabular data? DNNs is famous for not being good in tabular data. The best one is actually boost, cat boost, etc. And once you train DWNs on some collection of data sets, you actually, on average, we have the best average rank compared to attributes, cat boost, and transformers. Yeah, so, of course, you need to expand this to more data sets, that's another thing.
That's like an understanding question. So when you have like three lookup tables connecting to one lookup table at the next layer or something, what is the connection? Like, you concatenate the outputs or something? Or
They
you
don't
add
have
them?
bits inside. So exactly this, you just concatenate from an address and address.
Okay.
And then concatenate again, just concatenation. Yeah, so in conclusion, WN is a radical departure from neural networks. You don't have any max at all, no multiplication, no addition. Addition only the end
Sorry, can you go back this
to
way?
a popcorn.
What were these experiments for?
This one was just trying out tabular data, the same tabular data we're trying for ASICs. But instead of doing for targeting ASICs, we just compare to attribute categories like GM and see how it performs against them.
Blue on?
Auto glow one is the framework to make this automatic. Because you can fine tune by hand, you can use auto glue one, which is have been shown to outperform everyone just trying to fine tune by hand.
I see.
We just set every model to have the best quality settings so they can train for hours and hours. Just give me the best model. That's basically it.
Okay, and your results are the first
First row.
row or first column?
First column, yeah. Yeah, the bottom just added rank, you rank it through one with the first, second, third. And average loss as well.
So for these problems, of course, we don't want any of the other kind of, these are the best, these are the only ones that could ever be put into like an FPGA or something, and only XG boost, right? None of the others would fit on a microcontroller, none of the, so these are, we do well on tabular data. We took some of the other smallest things that do well on tabular data, and with the comparison, basically ranking it for size and accuracy.
But basically, like, how many features and how large are the data sets here?
Vary. Number of classes, number of features.
Yeah.
The other data set is like 2,000 samples, data set 2 million samples.
Oh,
It's vary.
The million sample one, how many features are there?
The medium one, I think, is 700 features, something
I
like
see.
this. I don't remember the details too much.
Yeah, I guess one important thing is the features become serialized in the sense you combine them to become the address to the lookup table. So we can handle more features, it's not a problem.
But so can you do this using images?
That's the goal we want to do, but right now we can only implement like weightless neural networks for MLP style networks. There's something about the position independence during training that it does not convert at all.
The position of the what?
When you have this sliding window of settings, for example, position independence, or I have the multiple patches of transformers,
Yeah.
something
Or
happens
just
during
not
backpropagation.
not even a transformer, just like a conveyor.
There's something that happens during backpropagation that does not converge at all. And if you just try to go big, the model just learns the identity function and underfits.
Oh, weird.
And we could only
This is
get
something we're working right now.
50% accuracy on cipher 53,
Yeah.
was it?
Mhm.
Yeah, so it is not able to learn. I think, if 3 is like this, yeah, but if 3 is like this or somewhere else, that invariance that convolutional networks can learn, we are struggling.
So we need a new backpropagation style algorithm to try to make CNNs into something. But right now for MLPs, we have the state of the art compared to DNNs, DNNs, and everything else.
And even that is significant because there are these fully connected layers in most of the other networks. So at least for that, we have a good solution there.
Yeah.
For the rest of it, in order to learn that, we are working on it.
Yeah, so this was exactly the conclusion. We have the best results for MLP state of the art compared to thin every possible DNN. But we right now cannot do CNNs transformers. This is exactly what I'm doing. Some people in my lab are trying to do as well. Generalized weightless with CNNs and transformers. And just to motivate a little bit, Dr. John's gonna show a little application we did.
Yeah, so we do understand the limitations. We see some places where we do phenomenally well, and that place is relevant in this world as well because the nanojoule, nanosecond inference doesn't exist otherwise. So if you have to go to, intelligence integrated with sensors, and you want to do it fast, and you want to do it with a battery that lasts for an year, you cannot do any of the usual things that otherwise we are doing. And so this was an example where the tiny sizes that we can, so arrhythmia can be detected. There are convolutional models that get 96% accuracy. It's just that it will have millions of gates to do that. And we can do this in 2000 gates once trained with this methodology. And so we came across this technology which is plastic substrate, and it can, so this is a company called Pragmatic in the UK. US also there are things, but this fab, we made some connection with them and they were willing to give us a free chip that we could make with their technology. So we made a weightless neural network to detect arrhythmia, and their technology is flexible, it doesn't need packaging, it's a plastic thin film substrate, but it is 600 nanometers, not 5 nanometer and 22 nanometer and all the things you hear. So 600 nanometer, they cannot fit too much, they are still developing. So they can only fit, they said 10,000 gates, it will be better if your thing is less than 8,000 gates. So we made no other arrhythmia detector, any neural network will fit in that budget. But we are able to make a network for arrhythmia detection with 2,000 some gates. And when it is the low gate count, they are able to fabricate the chip, even better because when it is to the brim, they may have more errors coming in the fabrication. So this chip was made and tested and fully functional, and it was basically, it is a capability beyond what exists otherwise. So the company's objective is to do these kinds of things on something like a Band-Aid. And so throw away, and this technology is also more environmentally friendly in the sense the amount of water they use during fabrication, all of those are better than conventional silicon fabrication at this time. So they have their limitation also, they cannot put more than 15,000 gates yet, but it is indicating some potential for maybe doing chips which are not silicon and which are environmentally more friendly. This particular technology is not biodegradable, but we are also talking with another technology, some other folks who have like a 3D printing sort of technology on a ribbon, and you print transistors onto it, but this is a biodegradable material. So it will degrade by itself, so more environmentally friendly.
But there are transistors on it.
There are transistors that are going to put, but the transistor is that type of thing, it will degrade also.
The transistor is biodegradable?
Yeah,
Oh,
it is not silicon.
I didn't know.
But they can only put hundreds.
I see.
You cannot put billions of transistors.
Sure,
This
sure.
technology only allows them to put, hundreds of transistors.
How does it get power if it's biodegradable?
It does have, you do have to provide power, but I guess the battery has to become biodegradable as well.
Yeah, right.
But they do have, I can, one place you can check out is Northeastern just hired this professor who was in Scotland and who was doing this work. So he is in Northeastern now, and basically they have, they do a lot of robotics. And so for the sensors that are 3D printed, maybe I shouldn't say 3D, it is 3D printing, but it's not with any 3D printer you buy. He made his own printer to print these transistors and the sensors and onto this and this ribbon technology. So we are talking because he cannot put anything big. He only has maybe 1,000 transistors at the most. So something tiny like this can be integrated very close to the sensors. So they are making electronic skin for the robot, and we can have many of these. In other ways you couldn't do it. So there are some places these tiny neural networks will be very relevant and potentially very useful. So, and we do want to do everybody transformers and LLMs and all of those. So we are working on it, but at the same time, the success so far we have is on the tinier side, where there is no other technology to accomplish this. So we are very excited. There are challenges, plenty of them. I can't gloss over those, but it is interesting and exciting to be looking more into it, and we, hopefully in the years to come, we can deliver something that is more mainstream, more, hopefully.
No, I think there are plenty of applications in like AI for health that are very mainstream.
Yeah, exactly. Yeah, it can touch lives in many ways. So we are also collaborating with Professor Nanshu Du in the mechanical engineering department, who does e-tattoos, electronic tattoos. So that also, right now what they do is, they have sensors, they have these patches that you wear, and the sensors sense things. There is a Bluetooth device, you send it out to a phone or to a computer, and then the processing happens there. So the battery dies very fast because communicating with the Bluetooth, even it's still, the energy will drain. Whereas if we can do processing right there and only send relevant signals rather than the entire raw data, so the battery can last longer. Patients can be sent home with this monitoring device, which otherwise might have lasted one day, now it will last 2 weeks. You know, and it's useful. And so, yeah, we are looking at places where this can make an impact. Yeah, but very excited. Thank you for listening.
Okay, thanks.
Yeah, we can take more questions.
Any questions?
Any more? Yeah, yes.
Yeah, on like the graph with like the tabular data performance, do you know like a baseline of like a regular neural network on like some general purpose computer, like or like general purpose like FPGA configure or something? Like how did that compare?
Let's say in tabular data on FPGAs or just our regular DNNs, how much accuracy they get?
Well, for a, let us say we were to do this with a CNN, some DNN.
Oh, there's transformers there through precision. Tab, NN, and NN, fast AI tab, is transformers.
Alright.
It's the three rightmost columns.
Right.
But they will be a lot bigger too, right?
Yeah, they're huge.
Yeah, they are huge.
But these tables, we're not trying to be small, we just, what's the maximum accuracy you can get?
Yeah, so the last three are those. The third column, this one. This is probably the smallest, right?
Which one?
This XGBoost.
The smallest XGBoost. We limit WN to be at
Yeah.
most the same size as XGBoost.
Yeah, because on this one, for an ECG, no. Yeah, the Zachary put the microcontroller comparison.
Yeah.
The only thing that could go to a microcontroller on that eTAT2 was the first one. Nothing else would fit. So the first one, with a lot of engineering, we were able to fit it, and then, but the DWN is better. Yeah. So even though DWN introduced multiple layers, till then we only had one layer of lookup table. Many tables like this and a reduction after that. So DWN, it put many layers, but still we are talking 3, 4, something less than 10. Okay, not 100, not so many layers. So lookup is still very fast. Many only have 2 or 3.
The main goal of this table was not like to win in accuracy. Us winning was a surprise. But the main goal was to show that we do not lose accuracy when trying to be efficient. Because it's very famous for DNNs. When you quantize down the number of bits or go to 1 bit, which is DNNs, you just lose accuracy. But we are not quantizing down. It's a different type of neural computation, which is using lookup tables, which have a higher receipt dimension. So you can be efficient and be high accuracy at the same time.
I just wonder, so for DNN, usually we study what actually a DNN learn, and for the lookup table, I also wonder the same question, like what actually a lookup table learn, what's the feature inside a lookup table?
You can, like, there's work doing this for weightless, which you get a lookup table and just express, because it's just Boolean, you can express the whole logic function. But good luck understanding what the logic function is trying to do. The same thing for DNNs, a black box. You can express, you have the whole equation of DNNs, but what's actually inside, there's no way to do. What you can try to do is just increasing the inputs to maximize the activation of a neuron to try to visualize it. But understanding what's inside the neuron, that would be interesting.
I think they did have work that understand what inside one neuron, like they visualize like force.
Yeah, but it's visualizations, like it's not a true understanding of what's happening inside.
I mean, they have some visualization, like this neuron learn this feature, like learn the
Yeah,
dog way.
you have the input, you make that as the optimizable thing and trying to maximize activation of a neuron. And then you can visualize what's inside the neuron. You can do the same thing for this, but we never tried.
And I have one more question, like, so I think company like OpenAI, they said they spend $1 billion to change the current ChatGPT, and if they switch to use this technology, then basically they need to throw away the ChatGPT or something.
I hope so, that's that's what we're trying to do. But right now training is actually as expensive as DNNs. because GPUs are so optimized for doing multiplication that we don't need multiplications, just bitwise operations. They're not optimized for that. But if you were to replace GPUs with something that's optimized for bitwise operations and not multiplication, we're gonna be as fast as inference, like what have you.
No, my question is, if they already spent $1 billion to change something and then now they switch to this technology, then they cannot reuse the money they already spent.
Oh, yes.
Okay.
Well, yeah.
You can try to convert this to a WNN, but you're gonna fall in the same thing like you said, try to pull down a neuron and convert to lookup table. You're gonna be way bigger than you actually need to be.
So you should be able to train on CPUs, you don't need GPUs to train.
And we tried on CPUs, right now GPUs is better.
But there's no multiplication.
Yeah,
There's no matrix multiplication.
But you can do it.
yes, but you can do a lot of ranks at the same time,
It's
bed
just
size at the
the
same time.
parallelization that you're.
Yeah, parallelization. And GPUs are also becoming better because they are going down to 8 bits and 4 bits computation. So there are so many things you can do in parallel for 4. Maybe we will waste 3 out of the 4, but it is better than wasting 31 out of 32. Yeah, so it is, training is still challenging. We should build hardware like FPGA hardware that can train at the bit level and we don't waste anything or something like that. But now it is a challenge.
GPUs can make a concatenate operation that will make training so much faster.
I see.
Because we need to bit shift and align everything to make an address.
Yeah, when we did the microcontroller implementation for the e-tattoo, we had to do a lot of bit packing and a lot of cloud engineering in order to make it fit, because otherwise if you just use ordinary data types available there, we would be wasting a lot of space.
Okay, thanks again.
Thank you.